Wherever we look in the universe, we see spiral galaxies. 70% of all the galaxies that we see today have this spiral shape that show up in their stars and their gas that's used to make more stars. And in my opinion, they are the most beautiful object in the entire universe. You can just get completely lost following the spirals around. But can we explain how those spiral shapes form in galaxies? Nope. There is still no consensus among us astrophysicists for how these spiral shapes form in galaxies. And that's thanks in part due to the huge variation in spiral structures that you see across the universe. From 2 spirals to 3 spirals to 4 spirals, or ones that are so fluffy you can't even count the number of spirals. There's ones with bars running through the middle, some where the spirals come off the ends of the bars, and some with bars where the spirals don't attach to the bars. There's loose spirals, tight spirals, big stretched out tidal spirals. There's blue spirals and red spirals, spirals in pairs, and spirals by themselves, and even galaxies that look like they should have spirals, but don't. Explaining all of that variation is no small feat. And so while we do have a couple of different ideas for how spirals are triggered and form in a galaxy and why some have them and some don't, we still don't yet fully understand them. So in this video, we're going to chat about a few different ideas we have for what spirals actually are, starting first with the discovery of spirals and the winding problem. Then chat about the modern frontrunners to explain spirals, from density wave theory, SSPSF, and swing amplification. And finally, why none of these ideas explain spiral structure in galaxies fully. Now, sadly, when I make short videos like this, there's a lot of things that I do have to skip over, especially some of the sort of background knowledge that you need. But if you do want to brush up on your foundations of science knowledge, then why don't you check out Brilliant, the sponsor of today's video. Brilliant is where you learn by doing, with thousands of interactive lessons in maths, data analysis, programming, and AI. Brilliant is a learning platform that's designed to be uniquely effective. It helps build your critical thinking skills through problem solving, not memorizing. So while you're building real knowledge on specific topics, you'll also be becoming a better thinker at the same time. For example, maybe you've always been interested in science, but you don't have the maths knowledge or practice to back it up. Well, Brilliant's huge range of maths courses are built for learners of any level, like whether you want to brush up on the fundamentals or challenge yourself with advanced concepts. With it, you'll use formulae to solve real problems in business and everyday life and enhance your visual and spatial problem-solving skills. So to get started today and to check out everything Brilliant has to offer for free for a full 30 days, head to brilliant.org/Dr. Becky, or you can scan the QR code or click on that link in the video description down below, and you'll also get 20% off an annual premium subscription. So thanks again to Brilliant for sponsoring this video and for continuing to support this channel. And now let's dive in and chat about the initial discovery of spiral galaxies and what became known as the winding problem. So the first person known to have recorded the fact that spiral structure existed in the universe was Lord Rosse in the 1840s, who drew a sketch of Messier 51, known today as the Whirlpool Galaxy. Now, when Rosse made his sketch back in the 19th century, he did not know the true nature of what he was looking at. Like back then, they were referred to as spiral nebulae. So nebula basically being used to describe any object in the sky that was like a bit fuzzy, nebulous, if you will. So not like a pinprick of a star that was dead sharp, right? And the nebula were believed to be around about the same distances as the stars around us. In the 1920s, Edwin Hubble measured the distance to these spiral nebulae for the first time using a type of star called a Cepheid variable, a technique that had been pioneered by Henrietta Swan Leavitt. And Hubble found that the spiral nebulae were much further away than the stars were around us, prompting a massive change in humanity's worldview or universe view, right? That said, okay, our galaxy of stars isn't the entire universe. And actually, our galaxy, the Milky Way, is just one island of stars in a much bigger universe containing lots of islands of stars, galaxies. The spiral nebulae became spiral galaxies. Now, people's first thought was that these spiral shapes were solid, static structures that like all rotate together. Now, you think about what has to happen for the galaxy and the stars in the galaxy for that to, all rotate as one solid structure, is that the stars on the outskirts have to be traveling a lot faster, right? Because they've got more ground to cover in terms of distance to make one full loop of the galaxy than the stars further in the same amount of time. And later in the 1920s, Lindblad and Oort were studying the speed of nearby stars in our galaxy, the Milky Way, and found that the stars near the sun do take longer to orbit than the stars in the centre. For example, we now know that the sun is moving around the centre of the galaxy at 828,000 kilometres an hour, meaning it takes 230 million years to do one full loop of the Milky Way. Compare that to the star closest to the centre of the Milky Way that takes just 12 years to do one orbit of the centre. So because people were already starting to think, well, the Milky Way is probably also a spiral galaxy, the fact that we've seen that stars on the outskirts move much faster than stars on the inside in the Milky Way, then that's probably also true for these spiral galaxies, and they're probably these static structures that all rotate in this way. However, it wasn't until the 1960s and 70s that telescopes were good enough to test this in other galaxies, when Vera Rubin and collaborators showed that while the speed does increase as you go out from the centre of a galaxy, it also flattens out before you get to the edge. Now that result would also go on to have other massive repercussions for our understanding of the universe. It's one of the foundational results for the existence of dark matter. I've made a video about that before if you want to check it out. But the connection of those flattening rotation curves and the existence of dark matter wasn't made in the 60s. It took decades for all the puzzle pieces of dark matter to come together. No. In the 60s, people were bothered about what this flattened rotation curve meant for spiral galaxies. Because if the outer parts of galaxies are all moving at roughly the same speed, then the stars on the outskirts start to lag behind the ones closer towards the centre, and the spiral structure gets stretched out until it starts to wind tighter and tighter, and the spiral structure can eventually disappear. This became known as the winding problem, and it really was the trigger for people starting to think about other ideas and other ways that we could explain what these spiral shapes were. Which brings me to the modern frontrunners to explain spirals. There have been a lot of things proposed over the years, but only a certain few have sort of outlasted all of the observational evidence that's been collected. So let's start with density wave theory, which was first proposed by Lin and Xu in 1964, who said that we shouldn't think of these spiral shapes as actual sort of like real tangible structures. Instead, these spirals are more like patterns that are created by a wave. Like how you can wiggle a slinky and send a wave through it. But if you send those wiggles at a specific speed, you get a pattern of a wave out. So the spiral isn't a real structure. It's a pattern that the stars and the gas move through, just like cars moving through a traffic jam. Think about it, a traffic jam isn't a real structure, right? The cars are the real tangible objects, and the cars are not fully stationary in a traffic jam. They move through it and exit out of the traffic jam as more cars join from behind to keep the traffic jam existing. This is what the density wave theory explains for spirals. And just to be clear, the traffic jam is the spiral pattern and the cars are the stars and gas moving through it. Now, physically, the two-armed density wave spirals are the most stable, meaning that they're very long-lived structures, which could explain why we see so many spiral galaxies in the universe. Because once you've formed this pattern, it's hard to shake it. But what this density wave theory doesn't explain is how you form the spiral arm pattern in the first place. Now, there's a couple of other different ideas that do touch upon this, including SSPSF, or Stochastic Self Propagating Star Formation, which was first proposed by Muller and Arne in 1976 and built upon by Garola and Steiden in 1978. And it's the other big frontrunner for explaining spirals. The idea being that a galaxy will form a clump of new stars wherever the gas is densest, as galaxies are known to do. But then as the biggest stars in that clump start to die out and go supernova, that sends shock waves out into the galaxy. And because not all the stars go supernova at the same time, these shock waves get dragged out as the stars move and orbit the galaxy. Those shock waves clump together more gas so that more stars can form along those dragged out chains, and you end up with a spiral structure that then winds up again after a few rotations of the galaxy. So it's almost like we're back to the winding problem again with these really short-lived spirals. But the thing is, with SSPSF, right, you're not just limited to one spiral structure and then boom, you're done. It can create spiral structures all the time. And so what you really have is kind of like this ever-changing galaxy where the spiral structure is sort of like coming and going. It's very transient. And what you end up making are very sort of like messy looking spiral galaxies, what are known as flocculent spiral galaxies. Flocculent almost meaning fluffy, which is why SSPSF struggles to explain what's known as the grand design spirals that are super symmetrical with regular ordered spirals that are really prominent. So for the grand design spirals, the best way to explain them is the density wave theory, except we still don't have a way to trigger the spirals for density waves. That's where the swing amplification theory comes in, which was developed by Toomer, Goldreich and Lindenbell through the 60s and 70s. They said that because you have this differential rotation in a galaxy where the speed of the stars is different on the outside towards the center of the galaxy, then any change to that system can have a massive ripple effect that then gets amplified as the galaxy rotates. Now, that tiny change could be anything from the collision of two gas clouds, or again, a supernova, or even from a close pass with another galaxy that pulls more on one part of the galaxy than another. These only create tiny distortions, right, in your disk of stars, but the effect increases as you move outward because of the different speed of the stars, sending out a ripple that swings from low amplitude to high amplitude as a density wave. So we come back to this density wave theory of thinking about, what a spiral actually is in the fact that it is a pattern. But crucially, in swing amplification theory, the spiral pattern is not static. It too moves through the galaxy and can rotate around the galaxy because it was initially triggered by this instability, this change in the disk that then rippled outwards. So if we go back to our traffic jam analogy, right? The cars move through the traffic jam, but the traffic jam can also move along the road with the cars, perhaps at a slower speed than the cars are able to pass through it. In swing amplification theory, the spiral pattern moves through the galaxy too, but doesn't dissipate like a traffic jam. The pattern constantly gets amplified as more gas is concentrated in the spiral pattern and more stars form there. Now, despite the fact that from our observations, we now know that these spiral patterns in galaxy do have a pattern speed that they move through the galaxy with, swing amplification theory massively struggles to explain the big grand design spirals. And instead, again, swing amplification theory likes to make a lot of flocculent and messy spirals. Which brings me again to part 3, why none of these ideas explain spiral shapes in galaxies fully. Because in any science scenario where you've got lots of different ideas that could explain like a phenomenon, you have to collect data, right? You have to collect evidence. And so in this case, it's observations of spiral galaxies that can hopefully help support one idea or another. And as you collect more evidence, you hope that a clear picture starts to occur. Sadly, that's not what's happened here. So our telescopes over the past couple of decades have gotten better, and our simulations and our computing power have gotten better so that we actually have the tools to test a lot of these ideas, and yet we still have a very murky picture of what's going on. For example, think about the density wave model again, but the one where there's a pattern speed where the spiral pattern also rotates. Gas will get denser in the spiral pattern as it passes through, so you'll trigger new stars to form. And the stars that burn the brightest are always the hottest and the biggest, that don't live very long because they've got to fuse hydrogen into helium at such a rapid rate to counteract the crush of gravity inwards because they're so massive. And those stars are very blue in colour, as opposed to more long-lived stars that are much smaller, not as massive, which are redder in colour, kind of like the dying embers of a fire. So you should get a colour gradient from blue to red as the spiral pattern rotates. So if the stars are rotating and the spiral pattern is rotating, you can end up with what's known as the co-rotation radius, where the two are rotating at the same speed. Inside the co-rotation radius, the stars will be moving faster than the pattern, and outside the co-rotation radius, they'll be moving slower than the pattern. So inside, where the stars and gas are moving faster than the pattern, everything piles up at the back of the spiral arm and you get bluer colours there. Whereas when the stars and gas move slower than the spiral arm pattern, the pattern moves into the gas, forming stars at the front edge of the spiral arms. So people tried to test this through the 70s and 80s with all sorts of different data and claimed all sorts of different things. But then in 1996, Gonzalez and Graham showed that dust plays a big part here. Because there are so many new stars forming and because the biggest and the heaviest stars don't live for very long, there's also a lot of supernova going on when those stars die that throw out a lot of the heavy elements, aka dust, that blocks a lot of light. At least visible light anyway. If you look at infrared light, that can actually pass through the dust. And so it was Gonzalez and Graham in 96 that showed if you do use infrared light, you see this colour gradient in the galaxy Messier 99. And since then, many other studies have shown these colour gradients can be seen in local galaxies as well as distant galaxies observed with the Hubble Space Telescope. So while that all seems to favour the density wave theory and perhaps the swing amplification theory of spiral arms, there's always complications, isn't there? Because it turns out if you do look at a galaxy in, say, optical or UV light, it looks very different sometimes than it does in infrared light. For example, you can see a grand design spiral in the infrared, which shows older stars, but then in the optical and UV see a flocculent, fluffy structure with many arms made of younger stars. Or there's even cases where in the optical you see, say, 3 spiral arms, but then you look in the infrared, you only see 2. You'd also think that studying our own spiral galaxy, the Milky Way, would help here because you've got like a closer look at what the spiral arms are doing. But nope, our vantage point inside the Milky Way makes things a lot more complicated. People can't even agree on how many spiral arms the Milky Way has. Is it 4 or is it just 2, with those extra other 2 maybe just being like bridges or spurs? And so there've been, again, a lot of observations that have come out. Some that say, yes, it's density wave theory of the Milky Way, and some that say, no, it isn't, it's something else. Data from ESA's Gaia mission should help. It recorded the brightness, positions and movements of almost 1 billion stars in the Milky Way. The problem now is there's almost like too much data with too much complexity for us to actually parse, what's going on here. At least that was the conclusion of a recent review on this, which also pointed out that the data we have about the Milky Way currently seems to disfavor the density wave model. So what do we do when observations are confusing? We turn to simulations, which back in the 20th century were very much in favour of the density wave model. However, they were more simplistic models, right? The particles in the simulation were just sort of like static star particles, right? They were really just sort of simulating the effects of gravity. But now in the 21st century, with all the advancements in computing and simulations that we have, your galaxy can now be much more realistically simulated. So that instead of static particles, you simulate star formation and supernova and shocks and heating and cooling and all of the dynamics that are going on. And when people finally did that, they realized that the spiral structure didn't last very long at all. Again, it seemed to like come and go, and you would make a lot of like flocculent spiral structure with many arms that didn't last very long. Which was again very confusing, although there was some work by Fujii and collaborators in 2011 that pointed out that if you only simulate your galaxy with less than 1 million particles, then yeah, you do get these very short-lived, fluffy, transient spirals. But if you simulate a galaxy with more than 1 million particles, that is again more realistic, and you get these long-lived spirals that have these defined arms, like a grand design spiral. So it could have just been a question of running a more expensive simulation that takes longer to run on a computer. And it seems like nowadays with simulations, it's kind of just like, well, what do you want to start with? Because that's going to give you something completely different out at the end, right? Like, do you want to, trigger your spiral through a tidal interaction versus just a little disturbance in the middle of the galaxy? And how do you want to fine tune that? Because that's going to give you different answers out at the end. But I think one sort of general agreement that's come out of simulations now is that yes, density wave theory does seem to be the leading thing, but it's definitely swing amplification that produces the spiral arms in the first place. So because of all this diversity of spiral-shaped galaxies that we see out in the universe, the consensus today seems to be that there isn't just a single way of making a spiral galaxy. Because there are just so many different physical processes that can affect a galaxy in its 13 billion year lifetime to both trigger and maintain a spiral pattern. Some might be described by density waves, and some by the SSPSF model. Some might be swing amplified, and some might be triggered by these tidal interactions. Or maybe We've just not collected enough evidence yet to fully understand the big picture of spirals. Either way, the universe is going to keep on surprising us. So the speed of the stars at the outskirts of the galaxy is different from the speed of the stars on sort of, I keep wanting to say inskirts. I think that's why I'm tripping over this so much. I want to keep saying in due part. I think it's like due course, but it's like in part due. And that's thanks in part due to the huge amount of variation. The outskirts have to be moving a lot faster than the stars. Sorry, I just had a mind blank.